Good morning all. Today I thought I'd carry on with my lithium ion battery project where I'm putting these lithium ion cells in parallel and measuring the current flowing out of one into the other, or into both if I'm charging them, or out of both if I'm powering something. So these two cells I think are pretty much at the same potential. I can touch these two wires together. Nothing really happens because the positives are about at the same voltage. Let's just see what current flows between the two cells. Oh, there is a bit, 16 milliamps. Now, trying to remember which direction that's flowing in. I think if it's flowing from V in to V minus, V in plus to V in minus, it's positive. So it must be going from this cell back up to that top cell at the moment. So I've got the bits in here to make another one of these ammeters. It's an Arduino Pro Mini with the 2 rows of holes down one end of the board, an OLED display, and one of these INA219 sensor boards. So I'm just going to make another one of these up now. Right, I've made up the sandwich consisting of the OLED display, the Arduino Pro Mini, and the current sensor board. I just need to now stick a screwdriver between these wire twists, because at the moment they're going to be touching, separate them out, and then I can attach the programming header to the Pro Mini, which is this sort of angled header at the end here, and put some code in it. Right, that's the sandwich made up, and those twisted connections bent apart with a small screwdriver so they're not touching. Connector on, this connector on for power, 9 volts. This is on the raw and ground pins, and raw goes into the regulator, so that's regulated down to 5 volts. But for the moment I'm just going to plug 5 volts in on this USB. Lights have come on, yep, so that all looks good. Now I'll fire up Arduino and write the program into there. Now, did someone write a modified version that had averaging? Let me take a look. Yes, here we are. Look, in the comments for my 15-minute ammeter project, Spongman has said, Julian, try this. And there's a haste bin address. I added a weighted average that should increase the accuracy of your display and stop it from jumping around so much. Well, I'm just going to load that code in and see if it works. Yeah, thanks, Spongman. Let's see how we get on. Right, well, I've just loaded in Spongman's code, so yeah, that looks pretty good. Certainly not jumping around much because of the averaging, so yeah, that looks very promising. So what I'm going to do is power up both ammeters now and just compare them, and then I'm going to try and rig them up so that they monitor the current flowing in and out of these two cells. Let's give that a go. Right, so here's the setup. Here are the two ammeters. Now the one at the top has Spongman's averaging software in it. The one at the bottom is just unaveraged. It's just giving or pulling readings directly off the current sensor. So let's see what happens if I put these two cells in parallel, because they're connected together at the negative end, and they'll be connected through 2 of these current sense resistors, one and then the second one. So let's connect them together. Now you can see, of course, that with some averaging software this is slower to respond. That's completely expected, but that will settle down once the set of readings. I don't even know how many there are. You can take a look at the averaging code yourself if you want. I'll put a link to his haste bin listing in the description below. But there we are. We have the top ammeter reading minus 12-ish milliamps and the bottom one plus 11-ish milliamps. So what we've got is a transfer. Now I've got to think about this. I think positive means it's coming out of the cell because it's going into the plus V in and going into that cell. I probably would do this the other way around, actually, so that positive means that a cell is being charged. Oh, I don't know. It could be either, couldn't it? Positive could mean a cell is being charged, or it could mean that a cell is providing a current. But anyway, there's a transfer of current from one cell to the other. I'll leave that for a little while to settle down. The numbers do seem to be reducing, so we'll see how low that goes. Now, of course, if I'm going to charge these two cells, I need to connect a power source, constant current really, onto this link because I want to be able to see the current flowing through both current sense resistors, otherwise I'm not going to be able to measure the current, and this commoning link on the back here. So I really don't want this insulated wire, so I'm going to replace it with a non-insulated wire. Now, it doesn't matter if all the wires at this end touch together. It's these two cells are at roughly the same potential, so it's relatively safe mucking about at this end. It's only if I short these wires at this end around to the ones at the other end that there would be a problem. So let me just cut a bit of wire to link around there, and then I can put crop clips on here to actually start charging these two cells. Right, I've got my B3603 power supply here. Now set it to 4.1 volts. I thought I'd just limit it a bit lower than the maximum of these, just in case there's a problem. And I've also set it to 500 milliamps. I'm going to charge these at 500 milliamps. So these should go up quite considerably. These have dropped to about 5 milliamps now of charge or of current being transferred from one cell to the other. Current, of course, being the flow of charge. Is that what it is? Let me just check. Yes, Wikipedia says that current is the flow of electric charge. Now, you can kind of understand that if you've got current flowing from one battery to another, because one will be discharging slightly as current flows between them, and the other one will be charging. So you can understand that charge is being transferred between the two cells. But anyway, what I wanted to do now was I put a diode in there just in case this power supply doesn't like having a large current fed back to it. So positive on my power supply. I can't see what I'm doing here. We'll go to positive on the cells, which is this joining wire here. Negative on my power supply, which is here. We'll go right round to the negative side of there. Let me just touch that on, make sure nothing nasty happens. It didn't. So that should be it set up. So when I switch this on, we should get a flow of current into these two cells, and it should be roughly equal if these two cells have a roughly equal capacity. Let's see what happens. That is not on. That should be on. What's happening there then? Yeah, the output is on. Why am I not seeing that large current? Right, well, it seems that the reason nothing much is flowing in terms of current here is because these cells are charged pretty much to about 4.1 volts. If I raise that to 4.2, then the current increases a little bit. They're both negative now. Quite a lot more current being taken by this one than this one. But I think what I'm going to do, because it's very near the voltage that this is putting out, I think I'm going to actually discharge these into a load. So let's use this load. This is a 5-watt bulb for a car, 12 volts. So what's that, about 2 ohms? No, wait a second. Right, well, anyway, whatever it's drawing, it's glowing fairly dimly there. Really interested to see the huge difference between these two ammeters. I would have thought they would be roughly the same, given that these cells are going to be roughly the same capacity, but they're substantially different. Maybe I'll load the same code into both of these ammeters, just in case there's an issue there. Right, the same code is now loaded into both, so they're both fast responding. They don't have the averaging anymore. See that if I take that off. They just jump straight to the value that's being read. Now, when they're transferring current from one to the other, they are about the same, 5 or 6 milliamps. But when I'm driving my load, this bulb, they're very different. So according to my theory, which is, well, it's not a theory really, it's how it is, that the current that flows is proportional to the capacity of the cell. These two cells must have very different capacities. The only way I'm really going to know that is to put these on charge and then discharge them and measure the capacity. I should write these currents on, or I should at least calculate a ratio, a factor of one to the other, and just see if their capacities match up to the difference in the currents. Quite surprised to see that, really. Now, if you're asking yourself, what are the voltages of these two cells? Well, you probably shouldn't be asking that, because they're the same. We've only got 100 milliohms there and 100 milliohms there, and the resistance of these bits of wire, which isn't going to be much, and all the battery box connections. So yeah, the cell voltages are the same. So I mean, the only thing really that matters here is that I don't want to take them below about 3 volts, but they're lighting this lamp quite effectively at the moment, so I don't think they're anywhere near 3 volts. But yeah, very different currents coming out of them. Now, this ratio is not actually that far off 2 to 1. 60 milliamps and 120 milliamps would be a 2 to 1 ratio. So this one is supplying more current. We got positive currents because I've fed the battery connection into the V-in plus. So we've got a current flowing from this cell through the sense resistor to the lamp, and from this cell through the sense resistor to the lamp. But the currents are very different. So let's call this cell 1 and this one 2. And I'm expecting cell 1 to have double the capacity in milliamp hours to cell 2. So I'm going to have to put these on charge them up fully, and then do a full discharge of both the cells with the same parameters for each cell, and just see which one has the higher capacity. Back in quite a long time. Right, so let's disconnect that so that they're now just feeding current from one to the other. And I'm going to take these out and put them in this, which is a 2-cell charger, the Engineer Lee 300. I'll charge these. I think this has a discharge test mode. I'm pretty sure it does. Should do. That's 12 volts. I'll put that on my solar system and get a capacity measurement for each of these 2 cells. And what I'm expecting to see is cell 1 is about twice the capacity of cell 2, which I wouldn't have known, but that's the assumption from this, which is that cell 1 is providing twice the current of cell 2 to this lamp. Right, so these 2 cells are charging at 500 milliamps each. Cell 2, which I'm guessing is the lower capacity cell, has gone to 4.2 volts more quickly than cell 1, which is a little bit surprising. Let's check their internal resistances. Now, this thing isn't terribly accurate with internal resistance, but it looks like cell 2 might have a larger internal resistance, 125 milliohms against 95 milliohms. I've got a feeling this doesn't measure any higher than 125 milliohms, so maybe internal resistance also plays a part in this, but I don't know. I'm more interested in the total cell capacity, so I'm going to charge these up, wait till they're both done, and then discharge them. Now, while these cells are charging, this one's at 4.2, neither have finished charging yet. I thought I'd look at the resistance of this lamp. Well, power equals I times V, so the current is 5 over 12. R equals V over I, so that's 12 squared over 5. So I've calculated that the resistance of this lamp at 12 volts is about 29 ohms. Now, if you have a cooler filament, I think you have, is it a lower resistance? Yeah, so it might be a bit lower than that. But I just wanted to see whether this resistance of that bulb would be low enough that these milliohm readings of internal resistance of these 2 cells were at all relevant. Now, I mean, even if this cell were 250 milliohms, it's a pretty small number in comparison to this bulb, which might be about 25 ohms, something like that. So I think we can pretty much discount differences in internal resistance, giving rise to these wildly different current readings on my 2 ammeters of a ratio of 2 to 1. So it must be down to capacity. So I'm very keen to see what the capacity readings of these 2 cells are. Right, so they've both fully charged, and I started the discharge. Now, I started it on the left-hand one, number 1, earlier, which is why it's clocked up 106 milliamp hours, and this one slightly later. But you can see that the voltage of the cell 2 has already dropped lower with less capacity drawn out than cell 1. So it certainly looks like cell 2 is heading down to 3 volts more quickly, and therefore cell 2 would have a lower capacity. I don't know yet, so I'm going to let this complete the discharge, and we'll get the milliamp hour readings for both cells and see what they come out as. Right, both cells have finished their discharge. Certainly cell 1, the left-hand one, has the higher capacity, 374 against 275 for cell 2. Their voltages have crept back up. This one finished discharging first. It's gone all the way back up to 4 volts, which is pretty strange. They are both extremely hot, particularly the left-hand one, which finished discharging last. Now, I seem to remember that when lithium cells discharge, they're exothermic, so they give off heat. And when they charge, they're endothermic, so in theory they draw heat in and therefore should feel cold. Generally, I think the effect is very mild, so you don't generally feel it because other effects overwhelm that. That's really beside the point. But anyway, we do have a larger capacity for cell 1. I thought these cells would be better capacities than these, but they're pretty terrible, aren't they? 374 and 275. So I think the next test I need to do is to charge these back up. That's gone very high. I don't think this... Oh, maybe this recharges after its discharge. Yeah, maybe that's the reason that's shot back up. Maybe it does a discharge and then actually charges them both back up and holds the discharge value. Yes, they've gone far too high to just have recovered. I think they're actually actively being charged. Let me put them on my power supply and see what the relative currents are. Right, the first thing I'm going to do is put them in parallel and just see what the instantaneous current flowing between them is. And it's about 250 milliamps. Now it's flowing into cell 2, I think. And that's dropping quite quickly. That will drop below 200 milliamps fairly briskly, I would think. So cell 1 certainly seems to have more, now what would you say, charge, energy in it, and is this what's happening? No, I think cell 2 has more, doesn't it? Because it's going to V in plus, so this is showing a positive reading, so the current must be flowing from cell 2 to cell 1. Yes, I think cell 2 had finished its discharge first in the charger, and therefore it got more of the subsequent charge after the discharge had finished, because I think what that charger does, the Lithium, I think it recharges after a discharge. Anyway, I'll let these settle down a bit and then I'll put the power supply on and start charging these. Now this is quite interesting. We know that the cell 2 has the lower capacity, but here I'm discharging them into this bulb. The voltage is about 3.68. And there's more current coming out of cell 2 than cell 1. So you might think at this point that cell 2 has the larger capacity. But if I take off this bulb, we can see that there's still a transfer of current of 40 milliamps out of cell 2, 40 milliamps into cell 1. So that's skewing the figures. So you can only really do this test when the two cells have really stabilized within a few milliamps, or well, I suppose a few tiny amounts of volts of each other. Remember, there's only 100 milliohms here and 100 milliohms here. So with 40 milliamps flowing between them, we could calculate what their voltage difference is, because there's a 100 milliohm resistor there. In fact, why don't we do that? So it's vehicles IR. The current is about 40 milliamps. It has dropped a little bit now. So it's 40 times 10 to the minus 3. And the resistance is actually times 200 times 10 to the minus 3. Let's work that out. Well, that's 8,000 times 10 to the minus 6, so that's 8 millivolts. There's only 8 millivolts of voltage difference between the two cells at the moment. And I can probably show that on the DVM if I clip onto one of the cells up here. We've got 38.6 38.5. Now I'm not going to see 8 millivolts, am I? Let's clip onto the other cell. Oh, 38.6. Yes, I guess they should be one digit out. Is that 8 millivolts? No, it would be the next digit down, wouldn't it? So we're really not going to see 8 millivolts of difference. 38. It's actually dropped into a different range where we've got 3 decimal places now. 3.868 and 3.8. I'm going to have to force this range because it's right on the cusp. So I want the range that has 3 decimal places. Right, 3.876 and 3.8. Oh, that's more than I thought it was going to be. I was expecting 8 millivolts from that calculation. 3.869. Is that 8 millivolts? Actually, yeah, I think it is, isn't it? 3.869, and the other one would have to be 8 counts higher than that, so 3.875. No, 3.877, which I think it was, wasn't it? Yeah, so 8 millivolts of difference. Yeah, so if I want to use the relative current flow as an indication of relative capacity, then I'm going to have to wait until the current flow between the two cells has gone down to near zero. Otherwise, the numbers I get on these two ammeters into a load are skewed by that transfer of current from one cell to the other. So at the moment I've got 70 milliamps and 100 milliamps, so there's 30 milliamps of difference current flowing into this load, but there's also 30 milliamps being transferred from one to the other. When that gets down to 15 milliamps being transferred from one cell to the other, then I should, in theory, see no difference. These should end up being exactly the same. Perhaps I'll wait until that happens. Right, so now we've got a situation where the amount of current coming from each cell to this light bulb load appears to be quite similar. Actually, cell 2 is supplying a little bit more, 86 milliamps against 83, but all is not what it seems, because if I take that load away, there's still 18 milliamps being transferred from cell 2 to cell 1. So if we assume that that 18 milliamps, sorry, let me put this bulb back in, transfer from cell 2 to cell 1 is still going on, then actually cell 2's contribution to the bulb is going to be lower than cell 1's contribution to the bulb, because quite a lot of cell 2's current is being transferred to cell 1. It's a bit of an odd situation. Right, now we appear to have an almost identical amount of current coming from each cell going to the load. It's about 85.5 milliamps. It's jumping around a little bit. But again, we're not really balanced, because take the load away and there's still a 16 or 17 milliamp current being transferred between the two cells. But they're going to swap over now. As that current transfer between the two cells reduces, in fact I think it's just happened, you can now see the contribution of current from cell 1 is greater than the current from cell 2, or appears to be greater, but we've still got a transfer of current from cell 2 to cell 1. So I'm not going to be able to use these two current readings, or the ratio between these two current readings, as an indication of the ratio of the two cell capacities until the transfer of current between the two cells has gone to virtually zero. And that's going to take a long time, because this current transfer is going to be dropping off exponentially. So it's the current will drop quickly at first and then slow down. So this could take several hours for this to get to near zero. And until that happens, I can't get a ratio of currents coming out of these two cells to indicate a ratio of capacities. The two capacities being, I think this one was 375 and this one was 275 milliamp hours. So to accelerate this process, I'm going to connect a wire directly between the positives of the two batteries. What will happen? Infinite current flow? Well, not really, because these two sense resistors are 100 milliohms each, and the resistance of this wire is going to be not dissimilar, maybe a bit lower. So let's see how much that drops. Well, it didn't drop that much, so there's still, even with a dead short, of course it's not a dead short, across the two positives, we've still got a visible transfer of current through these two 100 milliohm resistors, because of course this wire is probably not much less than, I don't know, 50 milliohms or something like that. It will accelerate the process of transfer of current between the two cells, but not that much. Right, I've put a second shorting link between the two positives, and that has reduced the current flowing through these current sense resistors, hopefully with these three paths between the positives of the two cells, the red wire, the black wire, and the two current sense resistors in series. I'll get these two cells balanced a bit more quickly, so I'm just going to leave it like that for a while. So I'm going to leave this for a while now and go and sit out in the garden, because as you can see from this line of dots, it's actually quite nice and sunny outside. Come back in an hour or so and see where we are with these two relative voltages indicated by these two relative currents. And now, to get a really low resistance between these two cells, I've put my two crock clips from my meter probes on there and just clamped them together to try and get the lowest possible resistance path I can between the two cells, to try and accelerate this matching, I suppose, balancing, so that they have the same amount of charge in them. That means that these are pretty much nulled out, give or take a little bit of null error. Take that off again though, and that goes straight up back up to 6 milliamps. So they're still not balanced. That dead short across there would need to be left there for quite some time, I think. So after a little while with these shorted as much as I can short them, I have got now cell 1 indicating a higher current to this load, this bulb, than cell 2. There is still about 8 milliamps of transfer between the two cells, but if we sort of factor that out, so let's say that this is 100 milliamps and this is about 70 milliamps, so the ratio is 10 to 7. So we're looking for something like this. A ratio of 10 to 7 is the capacity of cell 1 relative to the capacity of cell 2, so I'll just calculate X from that. And that ratio gives me X, which is the capacity of the larger capacity cell, is 392. Now I seem to remember it was about 375, but you can see we're in the ballpark, and you can see that larger capacity cells in parallel with smaller capacity cells provide the lion's share of the current. But that's about as far as I can go today, I think, so cheerio.